we may start. It's 4 p.m. here in Krakow, 9 a.m. in Salt Lake City, Utah, and we have privilege to have as a speaker Dr. Jake'a Bergquista, who's working at the Department of Biomedical Engineering, University of Utah, Salt Lake City, who will present us a lecture on AI in cardiovascular medicine. A few words about the speaker. Dr. Bergquist received his PhD, I think 1 year ago, on the topic of electrocardiography imaging. Actually, he dealt with calculations of quantification of uncertainty, which is important part of artificial intelligence and machine learning, frequently neglected, to know the error and the sources of error, and to build models which can accommodate with errors and give us better predictions. By education, he's a biologist, but since several years he dedicated himself to computations, to computational biology. Gave excellent lecture 2 years ago in computing cardiology meeting, and we are looking forward for your presentation, Jake. Thank you very much.
Thank you, Dr. Sanak, and thank you everyone for inviting me to give this talk. I'm always happy to talk about these research interests. And so I think with that, I'll go ahead and get started. So just a quick agenda on what we'll be talking about. I'll give, I've already gotten such a good introduction, so I'll give a brief intro. Background on AI and cardiology, a couple of examples from our lab, and some ongoing projects that we're working on, and then I'll take some questions. So starting with that background, like Dr. Sanak said, I did my PhD here at the University of Utah, and I was kind of split between 3 different institutions here, which kind of gave me 3 different backgrounds. So SCI, the Scientific Computing and Imaging Institute, was one of my main homes, and that's where I got most of my scientific computing training and prowess. The Nora Eccles Harrison Cardiovascular Research and Training Institute, or CDRTI, is a long-standing institute for cardiovascular research here on campus, and so that's where I focused my research on cardiovascular medicine. And then I did my PhD formally under the Department of Biomedical Engineering. Specifically, I did my PhD in electrocardiographic imaging under Dr. Rob McLeod. But during that process, I also got to be involved in many different side projects, which involved several that involved machine learning, which is how I got into some of my more current projects. So I have no industry disclosures to mention, although I do want to disclose that I did use AI to help generate this talk. Specifically, I used ChatGPT 3.5 to help me organize the talk, and Illustrator's generative AI to make some of the icons that you'll see. So, if you're not using these for your talks, I'd suggest that you give it a try. ChatGPT is pretty good at telling you how it might be good to organize your talk, and the Illustrator's figure generator, while it's not always useful for specific scientific figures, it can give some good icons and pretty pictures. So with that in mind, I also just want to talk briefly about my biases. So I'm an engineer, not a clinician. I work with a lot of clinicians, but my clinical experience directly is none. So I defer to any clinicians in the audience if you tell me what it's actually like in the clinic, and I would love to hear that feedback as far as how to better translate these ideas. I'm also not a mathematician by training. A lot of the math I've kind of learned through self-study. So I don't always get the math perfect. And I use AI and ML primarily, and usually I understand how to do it. So hopefully I can convey some of that understanding here. And with that in mind, let's go ahead and get into a bit of a background on AI and cardiology. And specifically, I want to take a step back for a moment and talk about something which is the difference between machine learning and artificial intelligence, right? So AI, artificial intelligence, and machine learning, ML, get thrown around a lot and kind of used interchangeably. And I would argue that that's not necessarily the case. So one way that one could think about it is if we have the space of all of artificial intelligence, that includes many different approaches and techniques. And generally, although the definition isn't formalized or specifically established, the way I like to think of artificial intelligence is designing tools which can solve problems in a, quote, intelligent way. And here we have designing, which gives us the artificial part, and intelligence, which gives us the artificial intelligence. Right? So this is essentially designing computer tasks or tools that can perform things in ways similar to how a human might. Then within that, we could think about machine learning existing as a set of approaches within artificial intelligence. And the way I like to think about machine learning is a field of study in which algorithms can learn relationships from experiences or data, right? So the machine is learning something by being exposed to a large volume of data and examples. And I've seen some Venn diagrams that show it this way, where machine learning is completely within artificial intelligence. However, I would argue that there is perhaps some space of machine learning that doesn't apply to artificial intelligence. And then specifically for today, my talk is going to be focusing kind of in this realm, mostly about machine learning and artificial intelligence, and a little bit outside of that realm. And so with that out of the way, I want to introduce this concept of a model, right? And but what I mean by a model is it's some sort of process that takes an input and converts it into an output. So for example, we were just talking about what the weather is like between our two cities right now. And that could be the output of a model. And let's say specifically, we want this model to be able to tell me what the weather is going to be like today, right? So we want a model to predict the weather for today. This is a problem that's as old as time. And so we could conceptualize, okay, what sorts of inputs might be useful to put into this model to give us this prediction? So for example, we could look at yesterday and we could say, what was the weather yesterday? Was it raining? Was it cloudy? Right? And most people, if you tell them, oh, the weather yesterday was rainy and cloudy, they might have a pretty reasonable prediction for what the weather might be today. And they're applying in their head some sort of a model. Usually that model involves some set of assumptions, right? So the weather tends to be similar day to day. That's an assumption, right? There's some sorts of rules applied to it, right? So if it rained 3 days in a row, then you might say, oh, well, it's likely to rain again. And there's relationships, right? So if today is the first day of spring, then that might tell you something about what the weather is going to be. Or if yesterday was the last day of fall, that might tell you what the weather is going to be, right? All of these get incorporated into our model in order to allow us to predict what the weather is going to be today. And models can come in all sorts of forms, but perhaps the one that is more relevant for today's talk is a model that can predict if a patient has a disease or not. Right? So this is something that doctors are doing all the time. They're looking at patients and they are trying to decide, does this patient have a disease or not? And in their head, one way or another, they're applying some sort of a model. Now, specifically for this talk, I'll be talking about models which take a patient ECG or some other measurement of the heart's function as their inputs. And typically this setup looks like we have a doctor that is reading an ECG and deciding whether or not there's a disease. But underneath all of this, the doctor is applying a model. And most of the time when a doctor is doing it, they're doing a rule-based model, right? So this is a model composed of rules that can take this input and help us make a decision. So I promise we'll be getting to AI and machine learning a little bit later, but first we kind of need to explore what we mean by a rule-based model here. So a rule-based model can be generated or created by taking in some assumptions like physics, assumptions about various states and rules, and adding them together. And then once you have your rule-based model created, you can then take inputs and convert them into outputs, right? So let's take an example here of this ECG analysis pipeline, right? So our physics that we might incorporate is we know that the body surface ECG is a consequence of the bioelectric source that is the heart projecting to the body surface, right? So the heart is an electrical organ. It generates a bioelectric source. We can then measure that from the body surface. Okay, so that's one of the inputs to our model. Another input to our model are assumptions about what a healthy electric activity of the heart looks like, right? So we know that the heart is composed of several different chambers and electrical activity spreads from one chamber to another in an ordered fashion in the healthy conditions. And so that is an assumption in our model of what the ECG should look like when the patient is healthy. And then finally, we have some rules for assessing these ECGs, right? We go in and we can measure different intervals between the different waves or components of the ECG. And we can use those rules and relationships between these different intervals to make decisions based on what we're seeing. So that's all well and good, but maybe let's pick a specific example and walk through it, right? So let's say instead of just a generic disease, we want to know if the patient we're looking at has atrial fibrillation or not. And atrial fibrillation is a consequence of erratic electrical activity in the top chambers of the heart, the atria, in which there is no longer ordered propagation from the atria to the ventricles. And so there's this chaotic wave that is moving throughout the atria that causes irregular heartbeat, that can cause several different health complications, and is one of the most common heart diseases around the world. So let's go ahead and look at this first ECG, right? So based on our physics and our assumptions of our physics-based model, we know that there's a bioelectric source and it's giving rise to this. So we know that this ECG that we're looking at is the consequence of the electrical activity of the heart, okay? The next thing we want to do is say, okay, we assume that when the heart is healthy, we'll have these various different components of the ECG. So we should be able to identify them if this is a healthy case, right? So we can look and we can say, oh, there is a P wave, there is a QRS, there is a T wave. So we know that the P wave corresponds to atrial activity, the QRS corresponds to ventricular activity, and the T wave corresponds to ventricular repolarization, right? And we can see a P, QRS, and T for every different heartbeat in here. We can then go take some additional measurements and apply rules. So we can say, okay, we'll look at the R to R interval, the time between the different QRS complexes. We can look at the PQ interval. We can take all sorts of measurements and say, does this conform with what our assumptions are about what a healthy ECG should look like? All right, so, if you're a clinician in this audience, you might notice immediately that this one is, a very stereotypical, almost cartoon looking ECG that I've created for us here. And this is what a healthy ECG might look like. Okay. By contrast, let's look at this ECG down here and let's apply the same rules, right? So we already assume that this is a consequence of the bioelectric source being measured at the torso. We can go ahead and start identifying the different waves. And it's pretty easy to find the QRS and the T wave for a few different heartbeats, but we're not seeing a distinct P wave. So that's our first indication that something might be off here. Right, and then we can start doing some measurements of different intervals. And let's just look at the RR interval, the time between these bigger peaks. We can see that it's very irregular, right? So the heart rate here is not regular like you'd expect it to be in a healthy person. So from this, we can plug these two ECGs into our model and we can determine, does the patient in each of these cases have atrial fibrillation? All right, so in the top case, they don't, and in the bottom case, they do. All right, and that's what our doctors are doing every day in the hospital. There's a litany of different diseases that they are able to diagnose using the body surface ECG and rule-based models. Now let's think through one more example and try to apply a rule-based model to it. All right, so ejection fraction boils down to the fraction of blood that leaves your heart over the fraction of blood that enters your heart. So how, for every heartbeat, what is the fraction of blood that gets ejected? And a higher ejection fraction usually means your heart is performing efficiently, and a lower ejection fraction means that your heart is performing not efficiently. And below a certain cutoff, this can indicate heart disease, that your heart is not functioning properly. Okay, so ideally, if we could measure this using the body surface ECG, that would be amazing because the body surface ECG is very easy to measure, very inexpensive. You can measure it non-invasively. And understanding what someone's ejection fraction from this simple measurement would be an enormous help in diagnosing heart disease. So let's go ahead and look at an ECG more similar to what you might find in the clinic. So I'm going to show you ECG signals from several different leads, right? Leads 1 and 2, and then V1 through V6. And if you don't know which leads those are, it doesn't matter. Just think about them as different locations across the torso where the signal is being measured. And so here's an example of some of those leads. And we can see several different heartbeats there. So I'm going to show you this ECG. And then right next to it, I'm going to put one from another patient. And I'm going to tell you right now that one of these patients has an ejection fraction that is over 40%, which is we'll call our cutoff for being healthy. And the other one has an ejection fraction below 40%, which we'll call our cutoff for being unhealthy. I'm just going to pause for just a second to give everyone time to really look at them and see if there's anything you can really tell that's different about them that you might be able to use to guess which one's which. Okay, so now let's look at the answer. Okay, so the one that is on probably the left of your screen, that's the one that's healthy, has an ECG or an ejection fraction over 40, and the one that's on the right has an ejection fraction under 40. And we could perhaps comb through these and pick out different reasons why we think this might be the case, but this is actually not a very easy to do task clinically. And in fact, by traditional methods, doctors are not usually able to diagnose ejection fraction using the ECG alone. Usually they have to use some other type of measurement of the heart's function. And we can kind of think that this might make sense, right? Ejection fraction is a very mechanical component of the heart's function, whereas the ECG is the electrical component. And clearly the two are tied together, but the tie between them is not always very obvious. Well, it turns out that while clinicians are not typically able to do this particular type of prediction, machine learning models can. Okay, and machine learning models are different than the models we've been talking about before. Remember, the doctor is usually applying some sort of a rule-based model. So now we need to kind of understand, okay, what's a machine learning model and how is it different from these rule-based models we've been talking about so far? Okay, so remember, a rule-based model is one that is composed of physics and assumptions and rules, and it can take inputs and convert them to outputs, right? So in this case, it can take an ECG and convert it to a diagnosis. Now, in our case for a machine learning model, the use is very similar, right? A machine learning model can still take inputs and convert them into outputs, but the way it's created is much different. Okay, so if you'll remember in the beginning, I talked about how a machine learning model or a machine learning in general is a technique that can learn relationships based on example, data, or experience. So when we're creating these machine learning models, the first thing we need is a bunch of examples. Right, so we have input data. Let's say each of these blue circles is a different ECG from a different patient. And then let's say these targets are the known ejection fraction, right? So we have a bunch of data that already exists. We already know what the correct answer is. Now we want to take this machine learning model and we want to show it the inputs and ask it, machine learning model, what do you think the output should be? And it's going to give us some answers. And those answers probably aren't going to be very good to begin with. But what we can then do is we can say, okay, we can compare, we can compute the discrepancy. We can say how similar was the output of the machine learning model to what we wanted it to be. And using some clever math, we can essentially push the machine learning model in the right direction. We can say, when it's doing better, we can give it a reward. When it's doing worse, we can give it a punishment. And by iteratively showing it more and more data, and updating the parameters of the machine learning model, we can eventually get it to the point where it is able to take inputs and reliably turn them into outputs. But the thing to note here is that this machine learning model didn't need any assumptions about the physics or the relationships between inputs and outputs. It just learned all of those just by showing it enough examples. And a common, well, maybe not common, but the example that I like to think about is people who can determine the sex of baby chicks, right? So when you're farming chickens, you end up having many little chicks, and you need to figure out which ones are the males and which ones are the females so you can keep them separated. And it's not easy to tell, but if you take a person and you show them, hundreds and hundreds of, here's a baby chicken, this one's a male, this one's a female, this one's a male, this one's a female, this one's a male, this one's a female. By the end of a few weeks of just showing them that, they can reliably pick up a baby chick and tell you if it's a male or female. If you were to ask them how can they tell, they just say, I don't know, I just know, right? They've learned by seeing so many examples, they've learned the implicit relationship between the input and output. It's a fascinating human example of essentially machine learning, of being showed, just simply being showed enough examples that you learn the relationship. Okay, so let's talk about a few examples of this actually in use. Okay, so we're going to take our same example as before of we're going to be reading a patient ECG and we're going to be trying to predict ejection fraction. And specifically, I'm going to show you some results that we presented at Heart Rhythm Society 2023. And And this is by a group of me and some collaborators here at the University of Utah. So in our space where we're taking these ECGs and we're trying to determine which ones have high ejection fraction or low ejection fraction, so which ones are healthy or diseased, we can put a lot of different things as the machine learning model, right? The machine learning model, all it needs to be able to do is it needs to be able to take an input and convert it to an output. But the internal structure, what it looks like in there, can vary wildly. And just as an example, some common structures that are used in image analysis, they can look something like this, where you have something called an AlexNet structure, which uses a bunch of convolutional layers, a VGG structure, residual blocks, dense net structure. These are all names of established machine learning models that just have different internal workings, different ways to relate the input to the output. And the thing that all of these share in common, these pre-existing architectures, is that they were designed with specific tasks in mind. And oftentimes that task is image classification. So they take in something like an image, and they're asked to classify, is this a cat or a dog? And of course, here's the picture of my two huskies that I have to include in my talk, right? So these pre-existing machine learning architectures of all different shapes and sizes, many of them were designed to classify images, take images as their input. But we want to take in ECGs as our input and have them tell if it's a disease or not. Right? We want to know if we can use these exact same architectures because they're already well studied and well established in image analysis, and use them for ECGs. But what do I mean by an ECG? Well, I don't mean the paper trace. I don't mean we're going to take a picture of the ECG. I mean, we want to actually work with the raw recorded signal data, right? So if we were to zoom in on one of these ECGs, it would look something like this. And under the hood, if you look in your medical system, when it's recorded by the ECG recording device, this is what it looks like, a bunch of data, right? And if you ask the people who run your hospital nicely enough and pay them enough money, they will give you this raw data. You can then encode the different values. You can essentially say, okay, for each different voltage value that I've recorded here, I'm going to assign that to a color, right? So larger values are going to be closer to a light color, and smaller values are going to be closer to a dark color. And now you can kind of construct your own image of an ECG where each individual pixel on the image corresponds to a different voltage for a different lead at a different time point. Right? Now we have something that these image-based networks, these image-based machine learning tools expect and can plug straight into them. Right? So for the purposes of this study, we happen to have a data set that consisted of ECGs and ejection fraction that was labeled using an echocardiogram for 24,000 patients. We then needed to split that into a training and testing set because if we remember, machine learning models need to be trained. They need to be showed the example inputs and outputs. So we took 90% of the data and set it for training, and 10% of it we set to use as a test. After we were done training, we wanted to see how well the machine learning could perform. So now what I'm going to show you here is the results after training various different machine learning architectures, right? So the first metric we'll look at is area under the receiver operator curve, which is just a general metric that tells you how well a classification task is working, where a higher number means better classification, and the closer the number gets to 0.5% or 0.5, the more likely it is that it's just random chance that would be producing the same results. And we want to look at the performance of several different machine learning architectures or several different machine learning implementations. And these are just different examples that we've pulled from literature of commonly available, commonly studied image-based machine learning network or architectures. So if we look at this first one here, ResNet 18, we see that it achieves an area under the curve that's somewhere between 0.8 and 0.1. ResNet 50 does the same thing. AlexNet is also similar, DenseNet similar, SqueezeNet similar, and VGG similar. They're all producing these fairly high area under the receiver operator curves. And in fact, in this next graph, I'm going to zoom in a little bit so we can see the differences a little more. So we can see that these pre-made, what we call off-the-shelf or readily implemented machine learning tools are able to predict ejection fraction at 0.92 or 92% area under the curve. right? So this is amazing. A lot of ECG diagnostic tools don't even perform above 85, right? So these machine learning algorithms are doing an amazing job at predicting something that most clinicians can't do reliably from the ECG. And the other nice thing is that once the machine learning model is trained, it can do this very, very quickly. Now, I also have the other statistics because area under the receiver operator curve is not always the best metric for showing performance. So we can see, here's the average values. We trained the networks 5 different times just to see how variable it would be. And we're still seeing, high area under the receiver operator curves, F1 scores, sensitivities, and specificities. I can come back to these numbers if someone's interested in them, but I did want to put them up briefly so people could look at it. And we see that this ResNet architecture, which is one of the kind of smaller machine learning networks, is actually able to predict the best across most of the metrics, right? So that was kind of one of our group's first studies into this field, is taking these image-based networks and trying to apply them to this ECG problem and saying, wow, it actually works fairly well. So the next thing we did is I presented this at Computing in Cardiology 2023. And this is a comparison of using machine learning tools to detect, again, low ventricular ejection fraction using individual leads. And what I mean by that is, in that previous study, we were using all of these leads of the common 12-lead ECG. We were specifically using the 8 unique leads. And we were using those to predict ejection fraction. What we wanted to do in this study is say, well, what if we only had one lead? What if we only had this lead or lead 2 or lead V1, right? How well would we perform? So again, looking at area under the curve, we can first look at the case where we use all leads as a comparison. And we can see this is using a different machine learning architecture, so we get slightly better performance, but it's still, in that 0.92 to 0.93 range. And we want to compare all of these results of just training and testing using just individual leads to this scenario where we use all of them. And we can say just using one of these leads, we're still able to produce area under the curves that are over 0.9, which is amazing, right? There's so many single lead devices out there, from monitors to your smartwatch, that if they could produce a diagnosis at this level of accuracy, that would be fantastic. And we can see that the performance varied depending on the lead. So lead 2 wasn't as good, lead V1 wasn't as good, V2, and then we kind of come back up as V3, V4, V5, V6. Oh, I forgot to show V6 here. And this was interesting for a number of reasons, right? We could speculate as to why the various leads are performing better than each other. But that's kind of, where some of our recent research has been leading us, is like, okay, now we know we can do these tasks. How can we investigate it more? And before I get into our current research, I just want to say, for more reading, I just searched Google Scholar for machine learning electrocardiogram and filtered it by 2024, and there's already over 5,000 articles out there. Peter Noseworthy and the group from the Mayo Clinic has been a pretty big inspiration for our group. We've based a lot of our studies on looking at the directions that they're taking things. But, it's not just them. There's many different groups now from across the world who are looking at doing machine learning on electrocardiogram data, right? So this field is kind of becoming bigger and bigger. There's several different devices or algorithms that are currently under review at the FDA. This is becoming a more and more popular field. So the next thing we'll look at is some of the tasks that we are currently working on, right? So if we remember back to this image classification task, right, we can say, okay, great, we can train this machine learning model to look at things like ECGs or pictures and make diagnoses or tell if it's a cat or a dog. But how? How is it doing it, right? How are we able to predict, or how is the machine learning model making its decision? Because it's not based on rules. It's not based on assumptions. It's based on some learning of the relationship. Well, the first kind of tool that people always talk about using for this is known as GradCam, which essentially is like looking at the internal structure of the machine learning network and saying, what areas of the input are you assigning high importance to, right? So if we were to take this network, we might look at one of these internal layers towards the end, and we'd say, blow that back up onto our input and say, what is the areas of importance? So for example, there's an article on Medium that kind of shows a walkthrough on this. And one thing that they do is they have a trained machine learning network that can either detect cats or dogs, right? And they show it this image of a cat and a dog. And then we say, what is the area of importance when you're detecting a cat? And what is the area of importance when you're detecting a dog? And just like you'd expect, when it's looking for cats, it highlights the cat. And when it's looking for dogs, it highlights the dog, right? So that's great to see, right? That makes sense. That's an explainability of the machine learning algorithm that, is very intuitive for us looking at it. So of course, the first thing we wanted to think about is, can we apply the same thing to the ECG, right? So if we look at an ECG like this, can we just add another axis, which would be the grad cam amplitude, right? And can we see what areas of the ECG the network is saying are important, where a low value means that it's not important and a high value means that it's highly important, right? So if we come back to one of our results here, where we used ResNet 18 in order to predict low ejection fraction, let's look at some examples of what the ECG looked like, whether the case was a false positive, false negative, true positive, true negative, what the ejection fraction was, and then finally what the grad cam was. So I'm going to show it to you just like this figure was shown here, where you'll see the ECG in black, and then the grad cam overlaid on it, where a high value is highly important and a low value is not important. And we're going to look at that for that ResNet 18 architecture. Okay. So I'll let this sit for just a moment. Okay. So there's a few features I want to point out here, right? The grad cam amplitude, at least to me, doesn't tell me a lot. All right, it's very variable from example to example. These are all different patients with different ejection fractions and different performance based on the network. And it's really hard for me to see some pattern. It's not always looking at a specific area of the electrogram when it's making its decisions. And it varies wildly between doing a true positive or a false positive, right? And this is one of the problems that we're dealing with in machine learning, is that it's really hard to explain why they work and how they work and what decisions they're making. So these results prompted us to then look around at the experts that we have here at the university and say, has anybody else figured this out for a different domain? Can they help us? And luckily we have Professor Tolga Tazizin here, and his specialty is machine learning development. And he actually has some papers from his group that are about just this very problem of trying to design machine learning networks in a way that makes them more explainable, right? And a brief overview, because this is what we're actively working on, we haven't worked out all the details, but a brief overview of how this works is we can take our typical paradigm where we have ECGs coming in, they're going into a machine learning model that's predicting whether or not there's a disease, and we can modify this slightly. We can say, can we make one model do augmentations? Right? And by augmentations, I mean it's going to change the signal somehow, right? And ideally, we want to set it up so that it's changing the signal to either make it look diseased or make it look not diseased. We can then add a second network that then tries to detect whether or not there's been any changes made, right? So this is called either the discriminator or the critic. This machine learning model, its whole job is to try and find out if something has happened to the ECG. And these two machine learning models are essentially fighting each other. One of them is trying to make modifications without being caught by the detector, and the other one's trying to detect anytime that the augmentation model is making a change. And if we construct this in just the right way, we can essentially emphasize modifications that show us what parts of the ECG are either looking healthy or looking diseased. Right? And so hopefully just by reconstructing how we formulate the machine learning model, we can get it to tell us what it's looking at just as a native byproduct rather than having to do some sort of a post analysis. And this is kind of where the brunt of our focus is. We have a couple of projects around this, and I would love to talk with anyone who's interested in talking about this, as well as several other areas related to leveraging our data better, leveraging data from different sources, and of course, investigating all of these aspects of how these machine learning networks perform across different socioeconomic and data set differences and a variety of other projects. And I think with that, I know I'm a little early, but hopefully that leaves us time for some questions. I'd like to thank everyone in our groups. I'd like to thank everyone here for inviting me and listening to my talk, and I'd love to take any questions.
Okay, thank you, Jake, for a very interesting lecture. We still have Professor Sanak, so maybe...
No, I just wish to thank, perhaps I got feeling that I understood something, but Claudia is much better than me.
We're still learning, so... all of us.
All right, so go ahead with questions. Thank you, Jake, again.
Thank you, Jake. Of course, I would like to ask our audience for questions. So if you have any question, please raise a hand, and then I will give you right to talk and to ask question and discuss with Jake. Do we have some questions from audience? Okay, we have first maybe Roman. Okay, I will give you a right to talk and even to see you if you are okay with that. Mr. Roman, do you have already? Yeah, but unmute your.
Okay.
Yes.
Now it's.
Yeah, and the next will be Daniela.
Yeah.
Okay.
Yeah.
Thank you.
Sorry to interrupt you. Perhaps if you Jake would close your presentation, we would see the participants and they raised hands. Thank you. Okay, fine.
Thank you.
Okay. Thank you, Jake, for the presentation. It's interesting, all these trials to make it use. We don't know how it works, and we probably will not know in the future, in close future, how it works. I wonder. I have some specific question. Have you, for example, tried on this first example to test your AI model on another sample, different hospital, different patient, whether you have the findings repeatable or not repeatable? So this is the first question.
Yeah, and that's the great question that you and the FDA and everyone is asking, because it's so important, right? We've seen so many studies where someone does some machine learning in their environment and then they take it somewhere else and it stops working. So we're currently in a collaboration with the Mayo Clinic where we exchange data with them, but we're not to the point where we have a sufficiently large data set from an external university to test it on. But that's something, we're actively in discussions with a couple of different locations trying to get that data. It's actually very hard to collect these large amounts of data, even though it's being recorded all the time from our institutions. Getting access to it is difficult and expensive.
Okay.
But I agree. It's a very, it's one of the things that we talk about all the time is we need to get external validation data sets. It's what our reviewers, it's what our grant reviewers are all telling us.
Okay, so maybe you can try on the Krakow data somehow.
Sure.
But another question is more general. For example, you showed that you have this decay of 92%. Do you think it's sufficient for a clinical diagnosis to have this precision in the data? We saw later that the sensitivity was 60%, was not much. Is it enough, or we should expect that it's 98%? Both sensitivity and specificity. How you feel in this? Thank you.
Yeah, I think that this is the problem. This is part of the problem with summary metrics. But I will say, for traditional ECG metrics, the sensitivity and specificity can range as low as 40, 60%. And the area under the curve for some clinical tests that are done with manual interpretation are already well under 80% area under the curve. So I think that as far as a number, 90% seems very good. Obviously, of course, we'd like it to be as close to perfect as possible. But I think that the problem is that, you know, in my mind, I'm not chasing a particular sensitivity or specificity. I think the more important thing for me is when it fails, why and where. Like, is it failing on people of a specific group, or is it failing under specific scenarios? Because if you can go to a doctor and say, you know, this thing performs pretty well, but here is the situations in which it is likely to fail, then I think that that's more powerful, because then that tells them when they can and cannot trust the machine learning algorithm. And I think that that's something that's missing from a lot of machine learning medical literature, is examining the failure cases and saying, and trying to figure out why or where the machine learning model fails, so that we can include that in the presentation of, you know, it does pretty good as far as the summary statistics, but, you know, if your patient happens to also have, you know, liver disease or, you know, something like that, then maybe you don't want to trust this, because we have that for some of the other tests that we use, but we kind of have this blanket trust in the machine learning that I think is not necessarily a good idea. I hope that got at what you were asking.
Thank you. Of course, you're right, but you know, if you can divide the group when the test fails and when the test is 100% right, so of course you want to have 100%. Specificity, sensitivity, which is of course not possible. You know, having these extra variables which fail, which make the test fail, of course, you know, explain something. But still, I understand that for some clinical use, we need to have a threshold, and it's not so easy to just leave it like now, because for now, when we do echo, so we of course may miss the right estimation, but at least we assume that it's 100% exact. So so thank you very much.
Yeah, I think just my final thing on that is I think that's the good question for I need the doctors to tell me how good they need it to be.
Yeah.
Right. And then I'll keep chasing that goalpost. If they tell me they need it 100%, then that's the target.
Okay.
Thank you.
Thank you, Roman. Also, we had a question from Daniela. Can you do we still have questions from Daniela, or okay? Also, yeah, are you there, Daniela? Yeah, we should, because I unmuted you and no, Daniela, we don't hear you right now, so we can come back to you later. But also Alexandra, Janczarska, yes, you wanted to ask question before. So yeah, now we can hear Alexandra, okay. And then we'll come back to Daniela, because for whatever reason we cannot hear you. Okay, so Alexandra, please.
Okay, hi. Thank you for being here. I actually have two questions. You touched on it in the previous one that was being asked. Of the inaccurate results from the ECGs, what were the, I guess, common denominators or the characteristics of the people whose ECGs were incorrectly interpreted? Did you have any information about those?
Yeah, so that's one of the studies where, you know, we put a medRxiv version out, but we were currently trying to get it published. So we took those various different off-the-shelf architectures, and we essentially said, okay, we divided them into correct and incorrect, and then we ran statistics on all of their various demographic, socioeconomic, all the other data that we had. And some of the interesting findings that we found is that patients who were sicker, right, who had, you know, maybe diabetes or hypertension or other heart diseases, the machine learning algorithm tended to do worse on those. And we can theorize as to why that was, but that was one of the findings that we found, is that a lot of these machine learning algorithms performed worse on patients who had more comorbidities. And then we also saw that it wasn't, different machine learning algorithms, they performed differently, right? They would get different patients wrong, which could be a benefit. You could maybe say, okay, I'm going to train 5 different networks, and then whatever they all agree on is going to be the correct answer. Hopefully, maybe using them to cover their differences. But they do seem to have some biases with respect to not only comorbidities, but also demographics and possibly socioeconomics.
Okay, thank you. And then my second question was, in the beginning of the presentation, you said that without AI, a regular ECG machine, as we know it, that is used in hospitals, can usually predict some sort of morbidity or some sort of erratic activity of the heart in about 85% of cases. What is that number after the involvement of the clinician? Does that, so by itself 85% of the time the machine can catch it? Do you have any figures on what it is after people have looked at it themselves?
Yeah, so I think to clarify, so there are some I guess I would call them AI, non-machine learning, but like some rule-based models for trying to detect diseases automatically using the ECGs. And I don't have the numbers off the top of my head what those performance are, but the actual performance of doctors trying to diagnose a myriad of different diseases from the ECG can be as low as sensitivity and specificity in the 60%. Depending on the disease, right? Some diseases are much easier to see on the ECG. For example, atrial fibrillation, one of the examples I chose, that one's usually pretty easy to find on the ECG. I don't want to misquote the numbers off the top of my head. But the involvement of the doctor doesn't necessarily, for some of these diseases, it doesn't necessarily make it better. One that's notoriously bad is detection of myocardial ischemia, which is kind of the precursor to a heart attack, right? When your heart gets an improper balance of blood supply and nutrient demand and waste removal and metabolic load. Imagine the people, clutching their chest. Diagnosing the early stages of that with a doctor looking at the ECG, even during the stress test, they can be as low as 60% sensitive depending on the case. And those opportunities where even though the performance can sometimes be that low, that's still the standard of care. Those are some of the cases where I think machine learning could come in and at least bolster or help.
Okay, thank you very much.
Okay, thank you, Alexandra. So now maybe Daniela, we can ask you for questions.
Switch the devices and now it seems to work. Can you hear me well?
Yes.
Barely.
Jake, great to see you.
Great to see you.
And also, yeah, you mentioned glasses frame with your T-shirt. That's an excellent amendment to the great talk. So thank you very much for that. Just to close the gap in my head, when you were showing the leads and the importance in the classification of ejection fraction failure, so there was no V6 visible. Was it at the end bigger than V5 and smaller than all leads? Just to make sure.
It actually, my slides got out of order, so let me show you real quick. Share screen, there we go. So here was the missing panel.
There was this V pattern.
Mm-hmm.
Oh, okay.
Yeah. So V6 actually performs comparably and in some cases a little better than lead 1. Which, if you think about it, where V6 is, we're detecting low left ventricular ejection fraction, so it's a left ventricular disease, and V6 is the one that's pointing most straight at the left ventricle. So that's just my top of the head, explanation for why that might be. But you also wonder about, lead placement error on these because that's a notorious problem, especially with the precordial leads. But yeah, it makes this weird V pattern. I don't know why lead V2 is so bad.
Yeah, it seems pretty bad there. So just in terms of all the methods that you use, so you tried out like the most common methods in the classification problems from the deep learning, and all of them provided actually more or less similar results. Did you fine-tune the parameters like number of layers, number of connections between layers, and like whatnot there, or you just used standard settings for them?
So for this particular study, the kind of the main drive behind the study was to use them as off the shelf as possible. Mm-hmm. So we made as little modifications as we could just to make it work with ECG data. And the main point there was to try and see just how well do they work out of the box. But I do agree that you could probably eke out more performance by doing some of this hyperparameter tuning with the number of layers and the complexity in there. We did not for this particular study just because it was moving on to a different project. For the second study where we actually see, you might see that the results are a little bit higher in the all leads case. This was based on a network that we designed based on what we saw in that first study. So we essentially took the ResNet architecture and broke it up a little bit more and kind of tried to optimize that to produce, slightly better results. And so, I think our record result right now is about 0.9308 or something like that. And that was based on a little bit, not exhaustive, but a little bit of fine tuning.
Oh, nice. Yeah. Thank you. And also maybe another one question. So you considered it to be a classification task. Were you thinking about it as a regression problem? Just the logic there would be if you try to quantitatively assess the ejection fraction in terms of absolute percentages, maybe your model will fail, but you will be able to define some margin, like being 40 to 50%. Then you will say, okay, my model is like not that super reliable, but everything under 50 or below 30, there's like 100% under the curve values. Would that be possible?
Oh yeah, certainly, and that's something we've thought about before. I think the part of what's we've been thinking about in that context, and we've even been thinking about in the classification task, is ejection fraction based off of echo is kind of the doctor using an informed guess, right? They're looking at it and kind of guessing what about the ejection fraction would be based on a lot of experience, but we were thinking, okay, if we do that, should we maybe blind some of the results that are kind of close to our cutoff? But I agree that the regression task would perhaps give us a little bit more fine-tuning control over, setting these bins. It is just a harder task. So we tried it a little bit and struggled with our data set not being large enough or diverse enough, because we do kind of have, we're missing a chunk of middle values. We have a lot of sick and healthy people, but we need some more people in the middle.
Yeah, clear. And just maybe your final take. So making actually everything inverse. So started discussing the results, and now to your background and how you feel about being an engineer, not a mathematician, not an ML AI engineer. So maybe you could also share with me and with the audience some of the lessons that you consider valuable on this path, starting the applications of machine learning and artificial intelligence to this specific application.
Yeah, I'd love to. I think one of the biggest things I've learned is that I try to surround myself by people who are smarter than me. And I'm really, I think that my main skill is I'm good at taking ideas from other people and kind of pushing them into one project. But the thing that's helped me a lot, because I'm by no means an expert in machine learning, like the fine nitty-gritty details of it, but I'm close enough with the people who aren't experts, and I keep them close to me so that they can kind of reinforce my own, strengths. And so I'd say, like, my general advice for being someone in this kind of engineering space where you're doing a little bit of clinical stuff and a little bit of deep math stuff is to, don't go it alone, right? Like, there's no reason you can't find, oftentimes these machine learning experts, they're excited that you have a real world application for them and they love to work with you. And so, find those people and keep them close.
Thank you. Thank you very much for all the answers. And as always, it's a great pleasure.
Yeah, it's great to see you, Daniela.
Bye.
Thank you, Dalina. Thank you, Jake. Do we have more questions from audience? I don't see. Maybe to sum up a little bit, I have my question, and it always came to me. What do you think? What is the superiority of machine learning over statistical models? And a next question connected with that would be when then use statistical models or machine learning or deep learning? What is your opinion about that?
Yeah, this is where my, I've got to make sure I keep my mathematicians close to me so that they can tell me when I'm saying something wrong. But I think that the benefit that machine learning models have is just kind of summarized in that the way that they're constructed, you don't need to go in with any idea of what's going on, right? You just say, here's a bunch of inputs and outputs, and machine learning model, you do whatever you need to do to relate them to each other. So it's, it's a very wide open problem as far as the solution that it can find. If you don't care how it gets from A to B, it'll get from A to B. Then of course that comes at the detriment is if you then want to go back and understand how it got from A to B, then it becomes much harder. As far as when to use, because the nice thing about statistical models is, they start from a more mathematically grounded perspective where you can assign meaning to the different steps a little bit more intuitively. But of course, that requires you to define things a little bit more rigorously, which can be difficult if you don't even understand where to start from. I think that where to use each one, it kind of depends on what side of that spectrum you need to fall on. If you need to understand more what you're doing and you don't have, the explainability analysis aren't working, then maybe you go to a more statistical or physics-based or rule-based models. Whereas if you just need the relationship to work, right, and you don't necessarily care as much about the internal workings of it, then machine learning can be powerful in that regard. And I think I would argue the thing that I've been thinking about the most lately is where they interface and where they meet with each other, right? And I'm not just talking about, because a common thing that'll get thrown around is physics-informed neural networks or PINs, but it's not just that. It's, how can you integrate the inputs and outputs of the different models in a way that's going to cover their differences or kind of help them work synergistically together. So that's a lot of what I've been trying to think about lately is, how can we integrate the machine learning and the more traditional modeling approaches together? Because I think that that's really where the future of things, at least in my perspective, is that to throw away all of the physical intuition that we have, especially when there are physics-based models and we're thinking about just replacing them with machine learning, right? The physics-based models have some important things in them that if we could leverage that in the machine learning model, then that would perhaps give us the best of both worlds.
Thank you. I think this middle way would be perfect for future. Do we have more questions from audience? Oh, we still have one more. I will give you a right. Yes, please, Jan.
Okay. Yeah, hi. I have a question regarding the data sets. Could you please elaborate a bit more on the process of obtaining the data sets? Was that process easy? They were already waiting there for you, basically, just ready to go? Or was that process painful and maybe these institutions only started saving some results in a manner that could be useful for machine learning algorithms? What was your experience with that?
Yeah. So from two perspectives, right? If I was a new machine learning scientist and I wanted to do machine learning in this space, there are existing data sets online, like PhysioNet and stuff like that, that there are lots of ECGs out there that are publicly available and you can go download and use. And that's relatively easy. I mean, you have to work on how to homogenize them and whatnot, but as far as from our perspective of how we got these ECGs that we have from our clinical system, on paper, it should have been very easy, right? Because the ECGs, I'm pretty sure that most hospitals, at least most hospitals in the US, a lot of them around the world, they're recording the ECGs, right? The ECGs that get recorded at the clinic are stored somewhere. And you just need to pay the company, in our case it was GE, We needed to pay them money to flip a switch to then allow us to download them. And that was it, right? Now, the devil's in the details. The actual getting that done, paying them the money was fine. They turned the switch. Getting them to then export all of the data back to about the year 2000, it was just a technical, it was technically difficult just because we had to orchestrate, because we had to take the data and de-identify it because it's technically private health or protected health information. But if the institute has already has a strong research focus, then in theory they also have techniques for dealing with this, and so that made it easy. But it did take us about a year or year and a half to actually finally get the data in a workable state. The nice thing about that, though, is for the ejection fraction data set, we have about 40,000 ECGs at the moment, over 20,000 patients. But we actually have about 1.4 million ECGs in our total data set that we've exported with a variety of different labels. And getting to that point, I won't say it was easy, but it wasn't insurmountable. It wasn't impossible. We had a team of like 3 or 4 people working on it pretty consistently for a little while, and then it got done.
Okay, thanks a lot.
Okay. Still, do we have more questions? Yeah. I don't see, but I think we really had a nice discussion. So once again, Jake, for a great talk, and hope see you soon in Krakow next year for conference. And thank you for our audience, and especially you, Jake, and see you in Krakow.
Sounds good. Thank you, everybody.
Thank you so much.